and taste. A place designed to host quality for your well-being without pollution or waste. A place just around the corner.
The biggest social benefit is that everybody gets fed healthy, clean food, and we can use it to remediate water so you can have safe water and safe food wherever you live. I've had no negative reaction to this idea whatsoever, a very positive reaction to it. And I think the idea is about to develop into reality.
The RepRap project is a project to make a three-dimensional printer, that is to say a device that you plug into the USB port of your computer and it prints out solid three-dimensional objects. It's to make that device and to make it both open source and self-replicating. So it's a 3D printer that can print out a significant fraction of its own parts, though not all of them. And it's open source, so if you've got a RepRap printer, you just download the design off the web for free and you can print another copy of it and give that to your friend. The parts that it doesn't print for itself are all designed so that they're universally available everywhere in the world for very low cost. The key thing about metals is not so much their strength. In fact, the metal we're working with is not particularly strong, but the fact that they conduct electricity very well. If we can print both in plastic, which of course is an electrical insulator, and an electrical conductor, then we can build three-dimensional electrical circuitry which liberates us from the necessity of making printed circuit boards. We can embed the electronics of a device within its mechanical parts. So for example, we could have an artificial limb which contained the electronics to drive the actuators in that limb embedded within what are effectively the artificial bones. Now, when I say electronics embedded, I should be clear that the RepRap machine makes the connections. It's not yet making the chips, which require much finer resolution than the machine currently works at. To make objects that are currently manufactured in conventional factories will extend that whole idea into virtually every solid thing that we have in our homes.
The introduction of highly sophisticated computer modelling technologies has meant that designing the shape and form of a building is now only limited by an architect's imagination. Leading architectural practices such as Foster & Partners are designing buildings to a level of geometrical complexity unheard of 10 years ago. However, while these forms can often be achieved through off-site factory-based manufacturing techniques, there are significant limits to the levels of intricacy attainable. For example, pouring concrete into a framework can go some way to fulfilling these ambitions, but the reality is that the achievable complexity is still limited. The manufacturing processes required to turn these complex building designs into reality have remained elusive until now. This may be about to change if current research by scientists at Loughborough University comes to fruition. The research group has been inspired by 3D printing, an additive manufacturing process. Here, information created from computer-generated models is exported to a machine which then builds up a model or a component, layer by layer. The virtual model is, in effect, materialized. At Loughborough, instead of using powder and glue, they are experimenting with concrete to create large-scale building components.
The research here at Loughborough University gives us tremendous opportunities. We are able to have a little peek into the future to see what construction technology will be in the next 5 or 10 years.
Concrete printing works on the basis of a highly controlled extrusion of cement-based mortar, which is precisely positioned according to computer data. The process has the potential to create architecture that is more unique in form, but crucially, components do not have to be made from solid material, and so can use resources more efficiently than traditional techniques.
We have shown how additive manufacturing can be developed to create large structures such as panels and walls, with precisely controlled voids within them.
For example, the section which you can see being manufactured here could incorporate all the service requirements of a building, such as pipes and cables, in one unit.
This process is capable of producing building components with a degree of customization that's not yet been seen. It could create an era of architecture that's adapted to the environment and fully integrated with engineering function.
Imagine whole sections of a building being printed and then assembled on site with their service provision already installed.
The Ultra PRT, short for Personal Rapid Transit, is basically a taxi crossed with a metro with none of the disadvantages.
I just thought transport was not done well. And I believe that if we thought about transport in a proper way, we would come up with a better way of doing it. And this is the result of that process.
Adam Ruddle, the PRT's lead engineer, explains how it works.
The passenger is going to come to the station, buy his ticket, and then when he gets to the vehicle, he will select the journey that he wants. He'll get into the vehicle. The vehicle will now be told by a central computer where it's going to. The vehicle then completely autonomously drives you from your start to your end station without stopping anywhere along the way in between. The vehicles that are going to a station will drive away from the main guideway into the station area. That means everybody who isn't going to that station carries on along the main guideway at the full speed of the vehicle. That way, you travel very quickly from your start to the end of your journey and are not delayed by anybody else's travel whatsoever.
It's quick, it's safe, it's easy to use, and it's pretty cool to look at. The Ultra PRT may just be the answer to India's heavily congested and potholed streets, and given how little it costs to build and how quickly it can be built, it may soon be headed to a neighborhood near you.
Over the weekend, Google made an announcement. They actually have bought the universe. No, but they have been secretly developing vehicles that can drive themselves on public roads, and they already logged 140,000 miles with their fleet of prototypes. In a press release this past Saturday, Google reaffirmed their position in the world. Google was founded to, quote, help solve really big problems using technology, unquote. One of those big problems is car safety and efficiency. Thus the reason to create new technology to improve autonomous vehicles. Recruiting top automotive engineers who have worked in the DARPA Challenges, a series of autonomous vehicle races organized by the U.S. government, Google has had their fleet successfully autonomously navigate everything from the Pacific Coast Highway to Lombard Street. Using video cameras, radar sensors, laser rangefinders, and detailed maps collected both from other vehicles on the road and Google's data centers, the cars can theoretically navigate any road. The World Health Organization claims that more than 1.2 million people are killed every year due to road traffic accidents. Google believes this new technology will cut that number right in half. The objective is to make driving more efficient, reducing braking and accelerating, which would ultimately save fuel.
Here at Virginia Tech University, where engineers from Torque Technologies and Virginia Tech have built a car that can drive itself.
Despite what it may look like, Odin's not driven by remote control.
There is no one in the driver's seat. Andrew's just cruising along, watching the computer.
To prove that, I took a ride myself. The car drove about 100 yards, made a 3-point turn, and drove back to its starting point.
So we've reached the end of this road segment and turning around. This is not a pre-programmed move. Depending on the geometry of the road or anything else here, it'll adjust to figure out the best way to go back and forth.
So how does it work? A complicated system of navigational devices, cameras, and scanners.
So there's a total of 7 mounted on the vehicle. There's 3 at bumper level. So what this is doing is it's sending out laser beams and scanning all around the car about 12.5 times a second. So these are looking for other cars, they're looking for people, they're looking for trees, any sort of other obstacles that you might find. The 2 on the front are looking down at the road. So they're looking for where the road is, where curbs are, where very small obstacles are, where potholes are, things like that.
So how many decisions is this car making per minute or per second while it's driving?
It's recalculating its path about 10 times a second.
The first thing you have to do is press this main button here, which switches on the system, and you have the ACC and LCAS buttons being enabled. We then set the adaptive cruise control, and you can increase the speed of multiples of 2. So here we are, I've set it at 68 miles per hour. You can see and identify a vehicle in front, and it is keeping 2 chevrons behind that lorry. And then with this button here, you can change the distance between you and the car ahead to effectively 3 chevrons, 2 chevrons, or 1 chevron. Then if I press this button here, the LCAS button, the camera now starts to see the lines in front, and I can feel the response. You'll see the steering wheel actually turning itself from the camera, monitoring the road ahead, watching the bends, and then feeding that input into the steering wheel. Now if I were to totally let go, which is obviously illegal, so I have to be very careful here, what the system does is it recognises that there's no steering input from me whatsoever, and after 10 to 15 seconds it would beep to say, look, I'm turning myself off, ultimately you're the driver, you're responsible for this car, this is just an assistance package. And there we go, it's just beeped, and I have to hold onto the steering wheel. It can feel that I'm now back in control of the vehicle for it to re-engage. Now this car is about to pull ahead of me. The system detects it, and I'm now starting to brake without me touching anything to keep a safe distance between this car and the car ahead. Now interestingly enough, I'm set to 68 miles an hour, but you'll see from the speedo that we're actually doing 55, because it says in order to stay in this lane and keep a safe distance from that car, I will have to reduce the speed accordingly. So what this means over a long journey, it effectively means that you've got somebody else supporting you, which means that you're more alert, it's less tiring over a long drive, you can look around more, check your mirrors more, and be more alert to drivers on the road. Now also, if I want to overtake and change lanes, but I don't indicate, what effectively will happen, and I'll show you here, if I go to converge lanes, the system beeps at me, tries to put me back into the lane. So if I do want to change lanes, I have to indicate, which makes me a better driver to those around me because they're seeing what I'm doing. And when I do indicate, what happens is the LCAS system, the lane keep, disables itself for a few seconds and then re-engages when you move into the next lane. Come off the motorway and you go below 45 miles an hour, the lane keep switches off. You've got to remember that the lane keep needs both of the lines on the motorway to be able to operate. If it can't see either of those lanes, it'll turn off anyway.
Replacement of human labor with machines. At the core of the economic system itself is the mechanism of labor for income. Our entire economic system is based on human beings selling their labor as a commodity in the open market. If humans do not have the option to work for a living, then the monetary system as we know it is over. No one can buy goods if they don't earn money. Companies cannot afford to produce if the consumer has no purchasing power to buy anything. As John Maynard Keynes disdainfully pointed out, we are being afflicted by a new disease of which some readers may not yet have heard the name, but of which they will hear a great deal in the years to come, namely technological unemployment. This means unemployment due to our discovery of means of economizing the use of labor outrunning the pace at which we find new uses for labor. While politicians, business leaders, and labor leaders bicker over issues they claim are responsible for the growing unemployment in the world, such as foreign company outsourcing or immigrant labor, the real cause is going unaddressed in the public debate, and that is technological unemployment. Since market capitalism is built upon the logic of reducing input costs to increase profits, the inclination to replace human labor whenever possible by machine automation is a natural progression of industry. After all, a machine doesn't need to take breaks, it doesn't require health insurance or benefits, and it isn't a part of a demanding labor union. A simple glance at U.S. historical labor statistics by sector shows the pattern of machine automation replacing human labor definitively. In the agricultural sector, almost all traditional workflow is now done by machine. For example, in 1949, machines did 6% of the cotton picking in the South. By 1972, 100% of the cotton picking was done by machines. In 1860, 60% of America worked in agriculture, while today it is less than 3%. When automation hit the U.S. manufacturing sector in the 1950s, 1.6 million blue-collar jobs were lost in 9 years. In 1950, 33% of all U.S. workers worked in manufacturing, while by 2002 there was only 10%. The U.S. steel industry from 1982 to 2002 increased production from 77 million tons to 120 million tons, while the steel workers employed went from 289,000 to only 74,000. In 2003, a study was done of the world's largest 20 economies, ranging from the period of 1995 to 2002.